Let's talk about the invisible engine behind every single piece of software you use, algorithm efficiency. It's the secret sauce that decides if an app feels like pure magic or just a total headache. So what is this code that counts? Well, let's dive in.
You've definitely asked yourself this before, right? You open two apps, they basically do the same thing. One is just instant. It's snappy, it's responsive, it's a dream to use. The other one? Oh, you're just staring at a spinning wheel. It stutters and it seriously tests your patience. The difference isn't some kind of wizardry. It's all about the code. And we have all been on both sides of this. On one end, you've got pure frustration and that dreaded loading screen. And on the other, you have the absolute delight of getting what you want, right now. We're going to pull back the curtain and see exactly what's causing this huge gap in experience.
Okay, so the whole thing starts with something called an algorithm. And honestly, the best way to think about an algorithm is just as a recipe. It's a set of instructions a computer follows to get something done.
Now, if you want the textbook definition, an algorithm is a step-by-step procedure. It takes some input, it follows a series of super clear, unambiguous steps, and it produces an output. It's exactly like a recipe. It takes ingredients, your input, and if you follow the steps correctly, gives you a cake, which is your output. And for any of these digital recipes to actually work, they have to follow these 5 rules. It's non-negotiable. It needs some inputs, it has to give you an output, every single step has to be crystal clear, it must eventually end, and every little instruction has to actually do something useful. If it fails on any one of these, you don't have a reliable recipe, you just got a broken algorithm. But just like in the kitchen, not all recipes are created equal, right? One recipe for a cake might take 20 minutes, another might take 3 hours. So we need a way to measure and compare our digital recipes. We have to become like performance critics for our own code. And we basically measure performance in 2 main ways. The first is time complexity, which asks the simple question, how long is this going to take to run? The second is space complexity, which asks, how much memory is this thing going to eat up? Now for this explainer, we're going to focus almost entirely on time complexity, because we're all about speed. So let's look at a really simple example here. This is an algorithm designed to add up a list of numbers. So it starts a total at 0, then it loops through every single number in the list, adds it to that running total, and then at the very end, it returns the final sum. Seems pretty straightforward, yeah? But how do we actually measure its performance precisely? Believe it or not, we can actually describe its cost with a mathematical formula. If our list has n items in it, the time cost for this little piece of code is exactly 2n plus 3. And I know what you're thinking, where on earth did that come from? Well, it comes from counting what we call program steps. Just think of a step as one basic operation for the computer. Let's go back and look at our code again. There's one step to set the total to 0, there's one step at the end to return the final answer, and there's one step to set up the loop in the first place. That's our plus 3. Now, inside the loop, which runs n times, we have 2 steps, adding the number and then moving to the next one. That's our 2 times n. So you put it all together and bam, you get 2n plus 3. The amazing thing is, we can mathematically prove the cost of our code. But walking around saying this algorithm is a 2n plus 3 isn't exactly catchy. So computer scientists needed a shorthand, right? A universal language to talk about performance, a kind of rating system for all our recipes. And this is where the famous Big O notation comes in. Big O notation is all about the upper bound, the absolute worst-case scenario. It asks, as your input size n gets really, really big, what's the one thing that truly affects the runtime? For our 2n plus 3, think about it. When n is 1,000,000, does that plus 3 even matter? Not at all. What matters is the 2n part. The time grows in a straight line with n. So we simplify it. We drop the constants and say its big O is just on, or linear time. And this gives us this amazing hierarchy of speed, a performance report card for our code. At the very top, the holy grail is O of 1, or constant time. It doesn't matter if you have 10 items or 10 million, the time it takes is always the same. It's incredible. But as you go down this chart to something like ON squared or quadratic time, things get really slow really fast. I mean, for an input of 1,000 items, a linear ON algorithm takes about 1,000 steps. A quadratic ON squared algorithm, it takes 1,000,000 steps. So a developer's job is always to stay as close to the top of this chart as possible.
And this is really the key thing to remember about Big O. It is a guarantee. It's you telling the world that no matter what happens, your program's runtime will not be worse than this. It is a performance promise, even on the absolute worst day. So how do we keep that promise?
So how do we actually write code that gets an excellent rating on that chart? Well, we use smarter tools. Over decades, computer scientists have come up with these incredible specialized data structures that are built from the ground up for high performance.
One of the classic pro tools is something called an AVL tree. Now, it's a type of search tree, which is already pretty good for finding stuff, but it has a superpower. It is self-balancing. It keeps a balance factor on every single node, which is basically its way of checking, hey, is my left side about the same height as my right side? This simple check makes sure the tree never gets all lopsided, which would totally kill our search speed.
So what happens when you add a new piece of data that messes up the balance? The tree actually notices. It identifies the problem, and then it performs this simple, lightning-fast maneuver called a rotation to snap the structure back into place. In a way, it heals itself to stay efficient. It's brilliant.
And the result of all this self-balancing magic is a performance of O of log n, or logarithmic time. And that, my friends, is an excellent rating. To get why that's so good, imagine finding a name in a massive phone book. You don't start at page 1. You open to the middle, see if the name is before or after, and then you throw away half the book. You just keep cutting the problem in half. That's logarithmic speed. Even with millions of items, you can find the one you're looking for in just a handful of steps. Another one of these super powerful tools is the heap. Now, a heap is a tree that follows one very simple rule. In a min-heap, a parent node is always smaller than its kids, which means the absolute smallest item in the entire collection is always sitting right there at the top, ready to go. A max heap is just the opposite. The biggest item is always at the top.
Okay, so why does any of this matter? Because these structures are the invisible workhorses of our entire digital world. You know that lightning-fast search in a huge database? Yeah, that's probably an AVL tree at work. That smooth Netflix stream that gets priority over your email downloads, that's a heap managing what's called a priority queue. These are not just academic ideas. They are fundamental to making the technology we use every single day actually work well.
And that brings us to the final and most important question. After seeing all this, is the secret to making software faster really just about buying a more powerful computer?
Nope, it's smarter code. It's all about choosing the right recipe for the right job. A truly efficient algorithm running on an old, slow computer will almost always beat a terrible algorithm running on a brand new supercomputer. The real performance gains come from intelligent design, not just from brute force. And that, right there, is the code that truly counts.